Cool, right? But is she right? Okay. A couple different forms you could write it in. Is there a couple different forms you could write it in, maybe? But it should be. Yeah, so just be careful. Maybe yours is right, and yours is, and this is right too, but they look a little different. I don't know.
Oh, is there a negative from
Down here, yeah.
Oh.
Is that okay then for you? Okay. I'm just trusting Julia. I haven't actually like looked at her answer and figured out whether it's right either. So we'll just trust. The point is, like I said yesterday, I warned you, right? That these are not always nice, and it's like takes a little while. It's not as easy as other derivatives. Yeah. And Adrian's going to answer this one too here. Eventually. Is C, did you guys get the right answer for C? Is this good? From 0 to 2 pi, I think I like. The graph of this, by the way, is fun, isn't it? Did anyone graph this, actually? Do you know what it is? I don't know. I mean, it's kind of crazy. It's not really Limason or Roadster. It's kind of both, isn't it?
Oh yeah, because it would have the two.
It's got maybe you can predict what the graph looks like. I don't know. What does it look like?
Oh no, wait, no, I don't know. Looks like a question.
Yeah.
So if the coordinate was non-zero, it was like 2
If it was 2, 5, or 6? I mean, that wouldn't be on this curve, right? I gave you a point that's on the curve. But you don't need 0, right? You just plug in pi over 6 to your derivative. I'm just telling you that if you plug pi over 6 into this, you get 0. Do you? Yeah, you can try it. You can verify that I'm right. I don't know. All right. So any Adrian, you have an answer yet for B?
No.
All right. Maybe we'll come back to that. You wanted to shout out some answers? Root 3 over what? Root 3 over 3? Okay. You tell me whether you get that or not, Adrian. Okay. In the end. Pi over 6 should be a nice value to plug in everywhere for theta, so I don't know. Hopefully you get that. All right, we're still doing polar coordinates today, some more. And today we'd like to talk about area. Kind of yesterday our focus was on derivatives, rates of change, and arc length. And today we want to think about area. Let me remind you, as we begin, of this area formula. This is for a triangle, as you know. And I'm going to orient my triangle this way, for reasons that will soon become clear. So if we call this, say, the radius, and this we call d theta, then, the angle change is d theta, then we could say, like, approximately that distance is r d theta. Can you say why? That would be r d theta. Keep in mind that it's not a straight line, it's an arc. Do you remember how to calculate the length of an arc? It's just r theta. So in this case, it's r d theta. 10 imaginary bonus points for Michael for remembering arc length. Yeah, in fact, it's wrapped up in the definition of radians. Yeah, theta is in radians, obviously. So, and by the radian measured of an angle, do you remember the definition of the radian measured of an angle? It's the ratio of the arc length to the radius. I'll write that down. The measure of an angle is the length of the arc, you could call it L or something, divided by R. That's the radian measure. That's why we like radians so much, is that they just kind of naturally arise, don't they? They're like a thing that's always constant in a, it doesn't matter what the circle size is, this ratio will always come out for the same for a given angle. So it follows from that that the length of any arc is equal to r theta if you multiply, provided again the theta is in radians. So for a very small theta, if we're calling this theta, or rather d theta, then it follows that that line is approximated by, and for, it is basically linear if it's a very, very small angle. Well, what would we call the area of this whole slice then? Maybe we would choose to call it like an infinitely small slice of area. So in the end, we get this for this small slice of orange area. We get 1/2 base times height, right? 1/2 r times r d theta. So this is one sliver, and you can already maybe see where we're going with this. We're going to be integrating inside. We're going to be finding area inside of some polar curves, and we're going to like sweep instead of from left to right when we're normally doing Riemann sums. We're going to be sweeping like kind of like in a pie. We're going to be creating a whole bunch of slivers that aren't rectangles, but they're triangles, and we're going to add them up. Okay. So with that in mind, we're going to think about it this way. So for example, if you're calculating the area inside of some curve in polar coordinates, then you start it, like we said yesterday, we kind of think of our limits of integration when we're doing the length of a line, we looked at even in the warm-up today, as going from alpha to beta or something like that. So now today, instead, I want to think, what would the area inside of this region be in polar coordinates? Well, you want to think about like a Riemann sum, right? It's a bunch of these things that we just talked about, a bunch of dAs, a bunch of slices of area. Well, this is the formula I just gave you for dA in terms of r and theta. And so we just slap an integral on that and integrate from alpha to beta. Where r, let's keep in mind, r is like r of theta, right? R is a function of theta. So how do you like that? Is that fun? You ready to find the area inside some stuff? Let's do it. So good. Coordinate. And then they launch it. And then they land. All right, are you good on the theory there? Just want to give you a second to digest it. Any other comments about that? Like I said, in calculus, we only have one game in town. Like, pretend things when they're small are lines, right? It's like what we do at every turn. So let's do our first one here. We get this nice cardioid to work with. Let's find the area inside of that. And the graph is already there. We should, by the way, I should take this time to, I think the sketch will have put the PowerPoint out. There's this other PowerPoint that has a whole bunch of like practice problems and like review on polar stuff. So you might want to check that out in the coming days if you like forget how to generate the graph of these in polar coordinates and like why is it that that equation has this graph and all that. I mean, I'd like you to have some knowledge of it. No one is going to be asking you like, look at this picture. Is that a cardioid or is that a Levinson or is that a rose curve? Or it's a lemniscate or whatever. No one's going to ask you that. But you should have like a working knowledge of how these things behave. I end up just like kind of thinking about plugging values in is what I think. Like if you plug in 0, just try it. You'll see you get 4, right? And if you plug pi over 2 in, you'll see you get 2. And if you plug pi in, you'll get 0. And if you plug 3 pi over 2 in, you'll get 2, pointed down. And then when you plug 2 pi in, you'll be back home at 4 again. So already you kind of have a feel for what this does. That's the level of knowledge I want you to have a little bit too. For you, David, yes, sure.
So the area is the integral of the radius?
The integral of the radius is just this function here.
Yeah,
So
1/2 r squared.
yeah, so it'll be 1/2 the integral from, what do you want to do? From 0 to 2 pi is fine, or again, any 2 pi that we capture would be fine. So I think 0 to 2 pi is the most natural one. And then, yeah, we're going to do this this is r squared d theta. Is that clear? That's what that formula on the last slide means. The integral from alpha to beta of 1/2 r squared d theta. Is that cool? Does that make sense? So you're integrating twice. I don't know if I buy that, but
1/2 r squared is.
Oh,
I guess you have to change the one.
yeah. I mean, maybe, yeah. Let's think about it. I just mean that, like, the r on the previous slide is like, just like when we said the integral of f of x, or the integral of y dx, or something like that. That's what that means. Here it's the function squared. Yeah, it's not real nice. In fact, I don't think we can even really access it by hand real easily. Though it would be a fun challenge for you to try. Again, doing this one by hand would require maybe a power reduction formula from trigonometry. So if you remember how to deal with it, because you'll have a cosine squared, and you don't know how to integrate a cosine squared, right? But you do know how to. Maybe you could like think about it from. Anyway, the point is we're going to do this in the calculator. But I just want you to like, just for your like own personal like love of the game, you might want to just play around with it later and see if you can solve this by hand. Because I think it actually poses an interesting challenge for us. You might actually have to return and think, can I write cosine squared as something with not a cosine squared? Yeah. Does that really ring a bell, the power reduction formula from trig? You don't have to know it. You don't have to know it. But. All right, I'm going to get my calculator too. You can beat me to it, feel free. Well, I'll check our answers in a second. You don't have to be in polar mode for this, right? You can use any letters you like. From 0 to, make sure your calculator is in radians though, please. You guys are way faster than me. What'd you say? 9 point, wait.
Like parentheses are really different from parentheses.
What did I? Oh, yeah, maybe I didn't get an extra set of parentheses there. I'm off by 2, a factor of 2, so that makes sense. $18.84. Let's get our AP rounding here. 850. Is that good? Yeah, you could clean this up a little bit beforehand, and you can whatever. But okay. Yeah. Did I not divide by 2? I think I did. Go ahead, call me out. Let's see here. No, I feel like I did. Yeah, I think that's okay. I think it's okay. I'm going to stand by it. All right, that's the very simplest problem I could possibly give you on as far as area goes. We'd like to also like ask questions like, oh, that's great. Look at that. I forgot I had that. Comes out to 6 pi, by the way, which is what you just said. Okay. I forgot I had all those pretty graphics. There we go. Look at that. Look at that. Okay. Sometimes we're also going to ask you some questions about area between polar graphs. So sometimes it's like our formula that we talked about earlier, right? If you have like a polar graph that's inside of another one at all times, then you could like think about them maybe not as top and bottom, but in terms of like outside and inside or something. So for example, here's one that I think falls into that category. We're looking at, so does it say, find the area that lies inside the circle r equals 2. I have them pictured here for you. And outside the cardioid that's here. So can you help me shade? Which region am I talking about? Inside the circle, but outside the cardioid. It's like the, how would you describe that? It's like the Batman logo or something, or what would you, I don't know. I don't know, it's not quite a Batman logo, but I want a name for that region. the shape of that region. I don't have a good name for it. Okay. The mustache region. Yeah. Okay. We'll go with that. All right. So yeah, I think, and again, I think the overarching thing we want to hear, that we want to really harp on today is like Riemann sums, right? Like how do those triangles look? At every stage in the game here, the triangles look like this. They can always be calculated in the same way. Oh, that was a terrible picture. Okay, let me try again. Here, I want to draw it kind of bigger too, so we can zoom in. At every stage, the triangles, like, let's take a sample value here. At an example of theta that we're going to choose, we're going to have like a region like this, and the thing we want to compute is this area right here, don't we? Like the difference, and it's pretty clear here that is the difference between the two triangular areas, yes? And that'll be the exact same thing no matter where I draw this along this curve here, right? It'll always be outside radius minus squared minus inside radius squared. It'll always be this formula. It'll be okay. I want to emphasize that because like right now you're like, I don't really appreciate that, but you will when that's not the case in another one, in another problem here. So sometimes it's this easy. Let's see if we can do it here with this in mind. And this picture in mind. I need some limits of integration too. So what's the very first theta that I want to consider for my areas here? I'm not feeling pi over 2. Not really. Yeah, don't I want to be pointed in this direction and calculate the difference between these two radii here? Yeah, I think I want to do that, don't I? So I think I want to go from 0 to pi. Now, there is some symmetry in this picture. You could also do what? 0 to pi over 2 and then double it, or pi over 2 to pi and then double that or something, right? So there's definitely some symmetry here that we can take advantage of too. All right, so then the outside radius is what? The outside function is 2, and the inside function that gives that radius is 2 times 1 minus 7. Okay, and again, let's go to the calculator. So yeah, I want to make sure we're saying we're basically just here's the other way you can say this. Okay. Yeah, it's basically just like you could do two integrals completely separate, couldn't you? Like you could calculate the area of the top semicircle first, and then subtract the area of the two hills. Okay. Yeah. No, 0 to 2 pi on this integral gives us all sorts of stuff. Weird stuff. Because when we get down to here, you don't have anything. 0 to pi, 2 pi, I mean, oh, pi over 2, what'd you say?
It's like, no.
Yeah, and then drop the 1/2. Yeah, exactly.
Yeah, it's like finding the area between two functions. You need to find the intersection points, and you integrate between the intersection points.
Yeah, in this case, it's 0 and pi are the theta intersection points. Yeah. Yeah, you'd have to solve to set them equal to each other and solve for the intersections. Yeah. We'll make you do that, don't worry. I'll do what Jack said and just do 0 to 2 pi over 2. Again, check my answer too. Okay, I'm getting approximately 4.858. I need to check let me just check what I typed in. 2 squared minus. Yeah, the parentheses might be messing me up.
I think it's easier to put it into the y into the r.
But I think that's right. Yep.
Easier to put it in r and then
Yeah, that's the other thing you could do is you could put it in polar mode and put it in R. Like I showed you on the screen there on the other slide, right? Like that. right? So you're welcome to use polar mode, and then everything does match with r's and thetas and stuff, or whatever. So you have some options. And then I don't have any instructions for this page, okay? Sometimes it's as easy as what we just talked about, and sometimes it's more complicated, okay? So let's show you an example of how this might work. So here we have just nice two circles. Sounds easy to me. And we're trying to find the area shared by the two circles. So that is the football-shaped region here, right? The area of that region. All right. And again, just to make sure this is like really clear in our minds what we're doing, we want to, if we're integrating from 0 here to like this, maybe this intersection will matter to us. Maybe we should find it, right? Like we were just discussing. What is that theta value right there? Because as we sweep around here, and we try and hit the edge of that red boundary, we're hitting that boundary, and that boundary is made up of different, it has like a different rule for that boundary depending on where we sweep our ray. And I want you to think about sweeping your ray like that, right? As you come around, you have like a ray coming from the origin, which you start at 0 maybe, and as you sweep, what's happening to the end of the ray as it hits the edge of the region. So I would like to maybe know that point there. What is it? Yeah, pi over 6 and also 5 pi over 6. All right, so that's going to be important, but not necessarily. I'm not necessarily sure how yet. So again, let me zoom in on this a little bit and really make sure this is clear. Okay. All right, so as we and that should be more symmetric than it appears, but as we're coming along here and sending out, like kind of as we're sweeping this way, we're getting these shaped triangles here, right? I shouldn't have gone out as far as I did, but you see what I'm saying. I'm getting these little triangles that meet the curve at this bottom white boundary here, right? Go. Redraw those. Right? So it kind of looks like that as we go. Until we get to the point at theta equals pi over 6. And then, now we're hitting it up here, aren't we? And these are the triangular pieces, right? And we can keep going, right, if we like. So do you understand how to calculate? Let's just ask, like, say someone says, how do you calculate the area of that yellow slice? The yellow piece. Notice that yellow piece has absolutely nothing to do at all with this function here that describes r equals 1, that circle. Do you see that the yellow piece like just doesn't have anything to do with this circle? It just didn't come into the picture. Like all we were using was the boundary from this equation. Here, let's highlight these. This one is using this boundary. Once we get up here, all we care about is r equals 1. But when we're between 0 and pi over 6, all we care is about the golden equation, okay? So with that in mind, do you understand how this is in fact not at all like the last problem? Even though we've got two curves and we're finding the area between them, so to speak. There's no like subtraction that's going to happen here between, you're not like finding one area and subtracting the other. Again, I really encourage you to draw the picture. Yeah, you're going to calculate two completely separate integrals. And by the way, why did I only go as far as I went? Because what am I going to do? I mean, you could go from 0 to pi over 6, integrate this guy, and then go from pi over 6 to 5 pi over 6, integrating this guy, and then add one more piece from 5 pi over 6 to pi, and that would work great. Or you could just, yeah, double our final answer, right? Yeah, Jeff. Yeah, so this white curve, maybe I should have drawn them in different colors. This white curve is r equals 1. And this this white curve down here, this is 2, r equals 2 sine theta, right? And so, like I said, as you're calculating this yellow area, it has nothing to do with r equals 1. Yeah. So here we go. The total area will be the sum of the two areas. We'll add, and then double. So we'll do it that way. So in green we have, or here we'll start with yellow, or golden. Sorry, I'm just having fun with my new board here because it's, okay. It's 1/2 the integral from 0 to pi over 6 times that function, which is 2 sine theta squared d theta. So that's that piece. And then plus 1/2 the integral from pi over 6 to pi over 2 of just 1 squared, if you like. Okay. And then again, like we've said a million times already, why don't you go over to the calculator on that? Okay.
I think we can do it.
I don't know that sine squared you can handle without a calculator unless you know your trig identities well. By the way, the 2 here makes me think I could maybe do some simplification too, right? So, all right, I'll do it, you do it, we'll come back together in a second and check our answers. By the way, I'll do each integral separately just so we can compare our answers that way too. So for the first integral, I get 0.182. I mean, doubled here. 0.181 plus, and the second integral, I'm getting. Wait for it. I guess this one we could do by hand, huh? I'm getting 1.047 approximately. Okay, I stored those in my calculator. So this is the exact answer perfectly, rounded to 3 decimal places. You guys agree with that? Someone out there did it? Anyone? Okay, thank you for the thumbs up. All right, good. All right. So we good on this discussion? There are lots of interesting things that can happen. Let's see if we can do one more, or at least before you go. We got a couple minutes here. All right. So did I give you a picture on this one too? Good. All right. So here's a rose curve and a circle. And we'd like to just at least shade the region that we even are thinking about right now. Find the area inside of the 4-petaled rose curve, but outside the circle. So do you understand that's 4 different things? But that's okay, whatever. I know how to, yeah. So it'll be all of these things here, right? Okay. So yeah, in the end, that's not a huge task. We can, in fact, actually, can you take even more advantage of the symmetry if you really wanted? You could go from like, you could just do half of a petal and multiply by 8 too if you wanted. There are lots of options, okay? Just to be clear. And all of them are correct, okay? All of the correct ones are correct, all right. All right, so which case is this? Do we want to start drawing some triangles here? Again, maybe I'll zoom in on that first petal, just the first petal, just to show us what's going on there. Okay, and then, yeah, once again, we're going to integrate from here to here, right? We want to like capture this whole area. So, so as we integrate, we'll be doing this kind of thing. Which case is this? And the area we want is like this piece here, out here, right? As we go. Which is the first case, isn't it? Yeah, it's just the first case. I guess we do need to know maybe what those intersection points are, though. We haven't figured those out yet. I think, yeah, hopefully it's nice again. Let's see. So it's 1/2 equals cosine 2 theta. Did I say that right? Yeah. So that's, so it's pi over 6, excuse me, pi over 3. But then, excuse me, I said that wrong. 2 theta is equal to pi over 3. So it's pi over 6. And we can just plug that in and see, I guess, 2 pi over 6 times 2. And, or actually plus or minus, right? And plus an infinite number of other things. But the ones we care about, negative pi over 6 and positive pi over 6, I think is what we want, okay? So I think we can do this. The integral from negative pi over 6 to pi over 6. Outer minus inner. We square them though, each one. Or cosine 2 theta is the outside guy. Minus the inside one. We need a 1/2 out front. Okay, that's the area that we're looking for one of these things. Yeah, and then we could multiply all that by 4. So I think that'll do it for us. You can plug that into the calculator and see what you get. Did I have one more example? I just wanted to see. No, I guess that's it. I'm trying to think if there are any other interesting things that'll come up. I mean, these problems can get pretty interesting, so I just want you to be aware of like the underlying principle that guides them all, and that's like drawing these triangles and thinking about what actually constitutes the areas that you're looking at. All right, so I'll calculate this here. Very calculator heavy stuff here. Actually, this one, the integral here comes, but I think you'd like to try that by hand. It'd be fun. By the way, in the homework last night, I didn't take any questions, sorry. Did they make you do that proof that I did at the end of class? No? It is a problem in the book. I just forget whether we assigned it or not. It's toward the end.
No, they had the problem.
It was there, though.
Yeah, it was
okay,
there.
yeah, I guess we don't assign it. I thought maybe we did, but. All right, I'm getting about 15.3 for the total area of all of them. 15.305. Anyone confirm?
Yeah.
Good. 15.306. I apologize.